Okay, this is the homework solutions for the section polynomials of a higher degree. So we've looked at quadratic equations, which are degree 2, because we have x squared. And you might ask, why does problem number 2 have x squared? Well, that's just to demonstrate the idea behind how you evaluate the end behavior. And as I said in the lecture, it comes down to whether something is an odd function or an even function. So you've really got, 4 scenarios here. It depends whether it's odd and even. So let's say even. And if you've got minus x to the even power, I'll put x to the e for even. If you got plus x to the even power, then we have the odd ones. So you've got x to the odd power and minus x to the odd power. So if it's even positive, the end behavior is going to be like this. So as you go to plus or minus infinity, in terms of x, your y value is going to go to plus infinity both ways. If it's negative x to the even power, then it's going to be end behavior is going to be like that. So you go to negative infinity both sides. X to the second, x to the fourth. Here you got odd. So if it's an odd positive x to the odd, it's going to look something like that. So the end behavior is you go to negative infinity when x goes to negative infinity, and you go to positive infinity when x goes to positive infinity. When you have a negative, you get something that looks like that. So all we have to do to answer these questions is look at the highest order term, which is 3, which is odd. And you can see I have a plus coefficient. So what you would do, how you would describe the end behavior is you can kind of draw it like this. Just draw a graph. And the end behaviors as things go away from 0 in the positive infinity direction and the negative infinity direction. So because this is positive x to the odd power, the end behavior is like this. It's just saying that this is what's going to happen as far as the direction. So that's how you'd answer 1. And then number 2, you do the same kind of thing. You draw an axis. Now, the highest order term is the squared term. This is the exponent, which is which exponent is the biggest one. But because we have a negative there, what that means is, again, if we got plus infinity in the x direction, negative infinity in the negative direction, the end behavior is going to be something like that. So if we had, if we had plus 3x squared, we'd have it going this way. It'll be like that. So it'll help. This end behavior will help us draw polynomials because we'll know which way the lines go as you go out in positive and negative infinities. Okay. Now the next one says use a graphing calculator to graph the function f and g in the same viewing window. Zoom out sufficiently far to show that the right-hand and left-hand behavior of f and g appear identical. So what we're doing is we're looking at the highest order term here, which is x to the 4th. It's going to be multiplied by negative. So you can see these two terms are basically the same thing. Now you've got these extra terms here, which mean this is going to affect the behavior around 0, x equals 0, but once you get out to really big, large values of x either way, this function is going to look very similar to this function once you zoom out. So I'm using my graphing program here to show how this works. So let's put the graphing program over here, smush it up a little bit so we can see it. So all you have to do is plot those two functions. So you have negative x to the 4th minus 4x cubed plus 16x. So that's the first function. Second function is negative x to the 4th. Now because these are even powers, we know that the end behavior is either going to go both to positive infinity or both to negative infinity. Well, because of the negative sign, we know it's going to have this downward frowny smile face. And if you graph those two functions at the normal magnification, you can see they don't look like they're the same, or they don't approach it. But if we zoom out in the x direction and we zoom out in the y direction sufficiently, okay, so I'm really zooming out here, you can see that the two functions do get closer to each other, and that stuff that happened around x equals 0 kind of disappears into the noise. You don't really see that. If I go back to normal zoom, you're going to see a big difference between them. But you can see that here they're both going in the same direction. They're pointing downward, and you can see that the right hand behavior, which is this behavior, and the left hand behavior, which is this behavior, are the same. So what you can do is just for this problem, just copy this graph down and draw an arrow to each one. So the red curve, you could draw an arrow that says negative 4x squared minus 4x cubed plus 16x. And for the blue curve, you could write that in just to show you that they are different, because you're going to do it with a pencil, so you're not going to have the color. Okay, so that's what they mean. Next one, find all the real zeros of the polynomial function. Determine the multiplicity of each zero. So what we're doing here is we are sort of getting a little somewhat ahead of ourselves, but we should be able to factor these without having as much knowledge as we need till we get to section whatever it is, 5, which is zeros of polynomials. So the whole idea behind zeros of polynomials is you want to figure out what values of t in this case will cause this to go to 0. You could just start randomly picking numbers and you might get lucky, but that's probably not the best solution. So what you do is you'd set the function value equal to 0. That means y equals 0. And then figure out t, which is the x variable. So because the reason this one's not so hard is because I've got this common factor, and you'll see both of them have a common factor. So the first thing you always do when factoring these things, polynomials, is see if you have a t and x, or whatever the independent variable is in each term, which I do in this case. So that means I can factor it out. So to get the resulting equation that once you factor out the t, is basically you divide every one of these terms by t, and what you have left over you put in there. So let's just put a little t under there. So if I divide t cubed by t, I get t squared. If I divide negative 4t squared by t, I'll get negative 4t. And if I divide 4t by t, I'll get 4. Okay. And you can see that if I take this t and multiply by each term in the parentheses, I'll get back to my original equation. Then what you have left over should be sufficiently easy that you can do it by stuff you've learned previously. So you'd ask the question, what two numbers multiplied together give me 4 plus 4? And so you'd say, well, I could do plus 4 times plus 1. I could take plus 2 times plus 2. So those are the obvious ones. Or you can have both negatives. So I could have negative 4 times negative 1, or I could have negative 2 times negative 2. And the sum of those two numbers have to add up to negative 4. Well, you can see the only one that's going to work where the sum of these two is equal to negative 4 is this last one. So I put negative 2 in both places. So you can see if I multiply this out, I'll get t squared. I'll get negative 2t, negative 2t, add it together, give me negative 4t. Negative 2 times negative 2 is positive 4. So that's factored. And when you have the same factor, you can rewrite that as t minus 2 quantity squared. So anything squared is that thing multiplied by itself. So when it says find all the real zeros of the polynomial function, well, the zeros are what values of t cause this product to go to 0. So you set one of the things equal to 0. If t is equal to 0, then 0 times anything is going to be 0. Likewise, t minus 2, if that equals 0, that'll make this term 0. Of 0 squared, just it's still 0. So to solve for the values of t, I'll add 2 to both sides. So my zeros, this is the factored form of the original equation. So the factors are t, t minus 2, and t minus 2. The zeros are the values of the t where the factors equal 0. So I set this equal to 0 or this equal to 0, solve for it. So the answer is the zeros are x, or in this case t equals 0 and t equals 2, or you could say it's 0, 0 and negative or 2, 0. Those are the actual points on the graph. So x equals 0, y equals 0. That means when I plug in x equals 0, I'll get y, or in this case t equals 0, I'll get y equals 0, or the value of the function. Same here, if I plug 2 into this original equation, it's going to be giving me 0. Let's just prove that. Let's show that f of 2 equals 0, question mark. Is that true? Well, you can go back to your original equation. So you'd have 2 cubed minus 4 times 2 squared plus 4 times 2. So that's just plugging it in here. You get 2 cubed is 8. 2 squared is 4. 4 times 4 is 16. And 4 times 2 is 8. And you get 0. So, it's not so obvious here, but once we factored it, then it is obvious that that's one of them. So it says determine the multiplicities of each 0. So let's go back and look at this. So there is no multiplicity for this 0. It's just one time. In this case, I have a multiplicity of 2 for this factor, because I take t minus 2 multiplied by itself. So that's what they're talking about when it comes to multiplicity, is do you have the same factor more than one time? You can have it 2 times, you can have it 3 times, you can have it 1,000,000 times if you want. Okay, the second one's similar kind of situation. You can see that you can factor out a t because there's a t in every one of those. So t to the 5th divided by t is t to the 4th. Negative 6t cubed divided by t is negative 6t squared. All I'm really doing is I'm reducing the exponent by 1. So 8t divided by t is just, 9t divided by t is just 9. Okay, now to factor this second part, you might say, wow, that's really hard, but it's kind of like a quadratic equation, because you've got something to the 4th, something squared, a constant. So what you should have, first step, is you're going to get t squared plus or minus something and t squared plus or minus something. If you had t cubed or t by itself, you couldn't do this, but because I just have the even t to the 4th, t to the 2nd, t to the 0, I can do this. And they ask, what two numbers multiplied together give me 9? Well, 1 and 9 are 3 and 3. Do 1 and 9 add up to be 6? No. Do 3 and 3 add up to be 6? Yes. So I know these have to be 3. And If I have both negatives, I still get a positive. If they're both positive, I get a positive. So in this case, because I need -6, I'm going to put a negative in there. Now, once you've gotten to this point, then you ask, can I factor this as well? And this is one of these cases where I don't have a middle term. So that's usually right. Well, actually, that's probably easier to just figure it out from here. Okay, so for this thing to be 0, for the function to be 0, which is where you get the real zeros, the first term can be 0. So this first term is 0 when t equals 0. That's kind of trivial, but the second one, you get t squared is equal to, or t minus 3 has to be equal to 0. And the same for the second one. So we're going to have this is going to happen twice. So if you add 3 to both sides, you'll get that. Then you take the square root of both sides, and you'll get plus or minus the square root of 3. So this one, you're going to have 3. Now these are the zeros. So the factors you go the other direction. So you get, let's see, so one solution is plus the square root of 3 or minus the square root of 3. So if you have t equals the square root of 3, let me get rid of that for a second. So if you get t equals plus the square root of 3, the corresponding factors, you're going to subtract that from both sides. Okay, so that's one factor. The factor associated with this 0 is not plus the square root of 3, but it's t minus the square root of 3. Likewise, if you take t equals negative the square root of 3, if you add the square root of 3 to both sides, you'll get t plus the square root of 3 equals 0. So that's the factor that corresponds to that 0. So ultimately what we have is t times this factor, t minus the square root of 3, and then t plus the square root of 3. That'll give you this, and then you get it again from this second part. So you get t minus the square root of 3, t plus the square root of 3. But you can see these are the same, and these are the same. So you'd rewrite this as t times t minus the square root of 3 quantity squared, t plus the square root of 3 quantity squared. So that's the factor. So what we can say is the zeros are t equals 0, t equals plus the square root of 3, t equals minus the square root of 3. We can say that we have a multiplicity of zeros at t equals minus the square root of 3 and t equals plus the square root of 3, because these are squared. We don't have a multiplicity of zeros at t equals 0. Also, if we want to plot these as points, it's going to be 0, 0, plus the square root of 3, 0, and minus the square root of 3, 0. So that's another way of representing the zeros, either as saying these are the values of t where the function equals 0, or these are the points on the graph. So that's the key thing here, is you find the zeros by factoring. If there are multiple factors that are identical, then you have multiplicities of zeros. And later on we'll find out that that is really critical for seeing what's happening with the function. If you don't have a multiplicity of zeros, then if you just have one zero, like here we have at t equals 0, the function intersects the x-axis. If you have a multiplicity of zeros, especially if it's even, it's going to touch the x-axis, but it's not going to go through the x-axis. If you had a multiplicity of zeros cubed, then you would actually, in that case, you would have an intersection of the x-axis. So odd-numbered multiplicities give you an intersection. Even multiplicities give you a touching at the axes. We'll see that later on, but right now we're just defining what multiplicity is. Okay, the next thing says find a polynomial function that has the given zeros. So this is again going from zeros to factors. So, let's say x equals -4, x equals 5. So those are the zeros. If I rearrange these to set them equal to 0, I'd add 4 to both sides. To get that, I'd subtract 4 from both sides. So these are the factors. So then all you have to do is say your function is equal to the factors multiplied together. Like that. Now, notice it says a polynomial function, because it doesn't say anything about multiplicity here. These are different. So, another solution, a more difficult solution, see if you had x plus 4 squared times x minus 5. In this case, they both have the same, these two have the same zeros. This one has a multiplicity of 2. This one doesn't, has a multiplicity of 1, I guess you could say. Okay, so that's how you do it. You take the zeros, make them into factors, multiply the factors together. So the next one, we have 3 zeros. We have x equals 0, we have x equals 2, and we have x equals 5. So we take those. Now this one, there's really no difference. We just have the factor is x, or you could say it's x minus 0 equals 0. But, this extra 0 really doesn't do much for you. Here you would subtract 2 from both sides to get that. Here you'd subtract 5 from both sides. So these are going to be my factors. X, x minus 2, x minus 5. So a polynomial function would be x times x minus 2 times x minus 5. And it doesn't ask you to do this, but let's go ahead. If I multiplied this thing out using FOIL, I'd get x times x is x squared. You get negative 5x plus 4x, that'd be negative x. And 4 times negative 5 is negative 20. So this is a polynomial function that has these given zeros. If I plug in 5, I'll have 5 squared is 25, minus 5. 25 minus 5 is 20. 20 minus 20 is 0. If I plug in x equals negative 4, it'll go to 0 as well. Okay, in the third one we have 5 zeros. We have x equals negative 2, x equals negative 1, x equals 0, x equals 1, x equals 2. So to make these the factors, you're going to add 2 to the both sides of this one to get 0 on the right hand side. You're going to add 1 to both sides. Here we don't have to do anything. Here we subtract 1 from both sides, and the final one is we subtract 2 from both sides. So these are going to be my factors. And the simplest case is just have those factors raised to the first power. So you're going to have the function, a function, is going to be x plus 2, x plus 1, x, x minus 1, x minus 2. There you go. I'm not going to multiply this out because it'll take more time than I really want to spend. That's how you go from the zeros. You go from the zeros to the factors. You multiply the factors together. Again, I could I could raise these to any power, and this crazy looking function would have the same zeros. They would have different multiplicities of zeros, and the functions would not look the same, but they would have the same x-intercepts or zeros. Okay, now the next one is a little more detailed because it's telling you what degree you want the polynomial. In this case, we use the smallest degree that we could given the number of zeros. And for the first two, it's the same as we had before because we have 2 zeros and a degree of 2. Here we have 4 zeros and a degree of 4. As long as the number of zeros equals the degree, then you do the same thing that we just did. So number 9, x equals -8, x equals -4. Add 8 to both sides. There's one factor. Add 4 to both sides. That's your other factor. Since it's a degree of 2, you can see that if I just multiply these two factors together, x times x is going to be x squared. That gives me the degree. So that's what I'm looking for. If it said degree 3, I could square this, or I could square that, and that would give me an extra x to give me x cubed. So this is for n equals 2. Let's just show you how you would do it for n equals 3. You'd say, f of x equals x plus 8 squared times x plus 4, or you could do x plus 8 times x plus 4 squared. Okay, again, degree, number of points, so they're going to be the same. So you get these 4 zeros, which give you these 4 factors. So these are the 4 factors. And then you just multiply those 4 factors together. X plus 4, x plus 1, x minus 3, x minus 6. And again, you can see I'm going to have this big long expression, but if I take the first term of every factor, x times x times x times x, I'm going to get x to the 4th. And that's the degree. Okay, so we'll do one where it's not that case. So in this case, you've got degree of 5. So we take the 2 zeros, x equals 0 and x equals -4, make those into factors. So this is a factor, and then you've just got x by itself. So my function is going to be x times x plus 4, and you can raise those to any power. We'll call this to the n power and this to the m power, and the only thing it has to be true is m plus n equals 5. So they want a function. So we could do x times x plus 4 to the 4th power. X is the first power. 4 plus 1. Or we could do x squared times x plus 4 cubed. We could do x cubed plus x plus 4 squared. We could do x to the 4th times x plus 4. But we have to have both of them. We can't just drop one of them off completely because we still need both of these terms. It's just the sum of the exponents has to be the degree. Okay, so now we're going to kind of put these together. We have our leading coefficient test, which we talked about first. We have the zeros of the polynomials, which we get from factoring. And then it says plotting sufficient solution points. So we're going to pick some extra points where we just plug the x value in and get the y value out. So let's just demonstrate this. So how many do we have? We have 3 of them. I think that's all we have for this. So we're going to need some graph paper. You'll need some graph paper at some point. But let's start here. So leading coefficient. So that's going to tell us what does the function look like as we go to plus or minus infinity. All you really have to do is look at the x cubed term and whether it's plus or minus. So you can see it's plus. That means it's going to look like this end behavior because it's an odd function. If it was negative x cubed, if I had a negative in front of x cubed, then it would be be this way. Okay, so we'll come back and use that later. So that's A. B is find the zeros, so we're going to need to factor it. Well, we were saying if you can factor out a common factor, which in this case is x squared. So if you take x cubed divided by x squared, you'll end up with x. And if you divide negative 3x squared by x squared, you just negative 3. So x squared equals 0 is one requirement, or x minus 3 equals 0. So if you take the square root of 0, you get 0. And if you add 3 to both sides, you get that. So my zeros are at x equals 0 and x equals 3. Now I have a multiplicity of zeros at x equals 0. We'll see how that affects things in a second. So before we decide to plot some points, extra points, let's see what we can say about the behavior of this function. Okay. So I'm going to use red here. And we'll go from negative 10 to positive 10. Same way in the y-axis. So this is x, this is y. Okay, so we know that the function is going to go out like this way. We'll readjust it later. We have a 0 here, and we have a 0 here. So we know the function has to come from this way. And it's going to come up, and because there's two zeros here at x equals 0, instead of going through, it's just going to touch the x-axis. It's going to come down, back down again, and then it's going to cross at x equals 3, like that, and then it's going to go up in that direction. So, these were just giving me an idea of what was going to happen. We have to kind of factor that into drawing this. So now that we've kind of drawn a rough sketch, the question might be is, where is that point? Because we could go down like this if we wanted to. It still would satisfy the requirements, so we don't know where that is. And we might want to find out, how quickly this function drops off. So we could either pick x equals -1 or x equals -2. Likewise over here we could pick x equals 4. We might do that because you can get, these cubic equations can change rapidly. So part C is pick some other points. So we're going to pick x equals -1. X equals, we'll go halfway between here. Well, yeah, let's go to 1.5. That's halfway between 0 and 3. And we'll do x equals 4, which is just to the right of where that crosses the x-axis. So those are the x values. So we're going to just plug it into the function. And the function, go back to the problem statement here, x cubed minus 3x squared. Okay. So we have x cubed minus 3x squared. Here we have 1.5, so we get 1.5 cubed minus 3 times 1.5 squared. And here we have 4, so we get 4 cubed minus 3 times 4 squared. So get out your calculators. Well, here we're going to have negative 1. Negative 1 squared is positive 1. So we're going to have negative 1 minus 3. So that's going to be negative 4. Next one I'm going to use my calculator for. 1.5 cubed minus 3 times 1.5 squared. Should be negative 3.4. And then the last one was 4 cubed minus 3 times 4 squared. Whoa, 16. Is that really true? 4 cubed minus 3 times 4 squared. Yeah, I guess so. Yep. Because 4 cubed is 64. 4 squared is 16. 16 times 3 is 48. 64 minus 48 is 16. Okay, so now, it's lucky we didn't pick anything bigger than that, because that one is going to be way off. We'll just estimate it. So 1, 2, 3, 4, 16 is going to be way up there. So basically, this thing is going to go up almost, not almost vertically, but it's going to go such that, you know, it's going to cross here somewhere. Okay. Now we can erase this part and actually plot negative 3.4. So we go negative 1.5, 1, 2, 3.4 would be about right there. So this thing's going to come down, go through here, loop back up, go to there, and then erase this thing. And you've got negative 4. So negative 1, negative 4 goes right there. So that goes through here, and then it's going to go down probably pretty quickly, just based on what happened on the other side. So let's go ahead and plot that. I'm going to have to zoom out at some point, but so we had x to the 4th minus 3x squared. And something's wrong. 3x cubed. I think, let me look back here. I've got the wrong equation. X cubed minus 3x squared. Okay. X cubed minus 3x squared. Okay. And let's zoom out in the y direction. So we can go all the way to 10. There we go. And in the x, in the x direction we'll go zoom out so that we get to 10. There we go. So we got 10 here and 10 there. And let's compare that with our graph. So here you see the x-intercept here and here. Because of the multiplicity of zeros, it just touches. This all actually goes all the way down to negative 4, but we're pretty close. The actual minimum, the local minimum here is not at x equals a half, but 1.5, but at x equals 2. You can see that this thing moves up pretty quickly. So I feel pretty good about that one. Okay, so we're going to do the same thing for these other problems. So 13, end behavior, same end behavior because you've got x cubed. It's just going to be faster because you got 3x cubed, but it's still positive x cubed. So that's end behavior. It's going to look like this because of the plus x cubed. It's the highest order term. Okay, the next thing, zeros. So you're going to take the function, set it equals to 0. we're going to factor out x because we have x in each term, but you can also see each term is divisible by 3, so you get 3x. So if you divide 3x cubed by 3x, you're just left x squared. Negative 15x squared divided by 3 gives you negative 5x. And 18x divided by 3x is going to give you 6x. In this case, we can factor this. So the first terms in the factors are going to be x because they just have x squared. Two numbers multiplied together give you 6 that add together to give you 5. Well, 3 and 2. 3 plus 2 is 5. 3 times 2 is 6. It's negative here, so I'm going to put negatives on both of them. It has to be both of them because I need negative 2 plus negative 3. And I also need negative times negative gives a positive. So from that, we can say the zeros are going to be when x equals 0. This 3 doesn't affect the zeros, it just stretches the thing out. X minus 3 equals 0. X minus 2 equals 0. So those are the factors. So when it's just 0, you just leave it there. Solve for x, you're going to add 3 to both sides. So my zeros in this case are x equals 0, x equals 3, x equals 2. That's where it's going to intersect the x-axis. Now because there's no multiplicity involved, at each one of these it's going to cross the x-axis. It's not going to just touch it. So let's put a piece of graph paper in there and see what we know so far. Okay, we'll still use the same scale till otherwise we can't use it. So we know the end behavior is going to be like this, and we've got a 0 at x equals 0, 1 at 2, 1 at 3. So we need to figure out some points to actually evaluate the function. So I think I'd pick x equals 1, x equals 2.5, x equals maybe 4, and x equals negative 1. So we're going to pick four values of x that are relative to the zeros. So part 3 or part C, whatever it is we're going to evaluate the function at negative 1. Evaluate the function, which is right here. And we know it's going to be a negative value because of the end behavior. We're going to do it at positive 1. We're going to do it at 2.5, which is between 2 and 3. And we're going to do it at 4. Okay. So I'm going to go back to my original version here, 3x. So you got to go back to the original. I guess you don't have to go back to it, but it's usually the best thing to do. So I'm going to write this down. It's going to be x cubed, 3x cubed minus 15x squared plus 18x. Okay, so 3 times negative 1 cubed minus 15 times negative 1 squared plus 18 times negative 1. So plug that into the calculator. 3 times negative 1 cubed minus 15 times negative 1 squared plus 18 times negative 1, negative 36. Whoa, is that right? Negative 3, negative 1, that's negative 3, and that's negative 15, so it's negative 18. Yeah, okay, so we're going to have to change the scale here in a second. Let's do the next one. So you'd have 3 minus 15, negative 12. Negative 12 plus 18 is 6. So it's going to be 6. we're going to do 2.5. 2.5 cubed minus 15 times 2.5 squared plus 18 times 2.5. Okay, I'm going to use my calculator for this. 3 times 2.5 cubed minus 15 times 2.5 squared plus 18 times 2.5, negative 1.875. And then for f of 4 should be a positive number. So we get 3 times 4 cubed minus 15 times 4 squared plus 18 times 4 is 24. Okay, so those are our points, but I'm going to change the scale here. The x scale is okay. The y scale, I'm going to go up to 30, I think. 36. So let's go to 40. How about 50? So each 2 units, each 2 marks is going to be worth 10. So 40, 30, 20, 10. Do the same thing on the opposite side. So we'll have, I'm going to put them over here, negative 10, negative 20, negative 30, negative 40, negative 50. Okay, so negative 1, negative 36 is going to be about right here. Positive 1 is 6, which will get you about right there. 2.5 is negative 1.75, that's about negative 2 right there. And 4 is 24, so that's going to be right about here. There's 20, 30. So now you can sketch in. So you're going to come up here, going to straight through because it's a single root. You go through this point, you loop it around. Go down through this, go straight through, goes to here, then goes back up through this point and continues on. So you can see my AND behavior is as advertised. Let's get a graphing program here. I want to zoom out so that it goes to 30 before I put my new function in. Okay. So the function was, I've already forgotten what it was. Go back here. So let's pull up. Yeah, I'm going to have to close that for a second so I can move this out of the way. Okay, just need to be able to see what the function is. So you got 3x cubed minus 15x squared plus 18x. Graph this thing, move it over there, go to the graph. So there you go. So this went up to about 6. This went down to negative 1.8 something, about negative 2. And for 4, which is about here, you'd have a value of 24. Is that right? So when x equals 4, it's about 22. 24. I'm going to check that number. Seems a little bit off. Let's just zoom in here. 24. No, it works out. Yeah, 24, 4. That's good. And if I go down to negative 1, oh, actually I didn't zoom out enough. That's why. I should have zoomed out a little bit more. There we go. Yeah, that looks more like it, doesn't it? Okay, so that makes me happy. Okay, the next one. Again, we can see there's a common factor, which is x squared and 3. So if we take f of x and we factor out 3x squared, so negative 48 divided by 3 is going to be 16, I think, right? Is that right? 48 divided by 3 is 16. Okay, so we'll get negative 16x squared plus x, pardon me, just negative 16. So you get negative 16 plus x squared. And I'm just going to change the order of those two. So you get 3x squared, x squared minus 16. And you can factor this. It's going to be plus or minus something, right? Because you don't have a middle term, so it's going to be plus something and minus something. It has to be the same thing. That same thing has to be a 4, because 4 times 4 is 16. So what you get is you'll get, for one thing, the end behavior is, so look at the end behavior first. Because it's even, the highest order is power is 4, so it's going to be either like this or it's going to be like that. Because it's positive, it's going to be this way. Okay, so that's the end behavior. The zeros, we're going to have 4 zeros, well, 3 zeros, where 3x squared equals to 0. Well, that's where x equals 0. Where x plus 4 equals 0, so the 0 associated with that factor is negative 4, and x minus 4 equals 0. Add 4 to both sides, you get x equals 4. So what's going to happen is this thing is going to come down, go through the x-axis, because there's a single root here at negative 4. It's going to come up to 0. That's the next larger number. It's not going to cross it. It's just going to touch it, and then it'll go back down, and then it'll cross at positive 4. So that's kind of the general shape. So the question is, what numbers do we want to pick? Okay, so let's draw a graph here again. I've just kind of sketched it out here, and we may have to adjust the y-scale once we plotted a few things. So we've got x-intercept of 0, negative 4, positive 4. So I would pick, say, 5, negative 5, positive 5, negative 2, positive 2, because those are kind of outside. Those 2 points here are outside. These ones are in the middle of the 3 zeros. So if I'm going to evaluate the function at negative 5, I'm going to evaluate the function at negative 2. We already know what it is, 0. F of positive 2, and these should be the same because you have the symmetry. You're going to have symmetry around the y-axis, and positive 5. So the function is, where is it? Go back to the original equation here somewhere. So we have the function is negative 48 x squared plus 3x to the 4th. Okay. So we get negative 48 times negative 5 squared plus 3 times negative 5 to the 4th. The next one is negative 48 negative 2 squared plus 3 times negative 2 to the 4th. And we won't have to work these out, but I'll just show you why they are symmetric to the previous one, so we don't have to do 2 calculations here. And the reason is because we're squaring them, it's all to the even powers. So this is squared, this is to the 4th power. So these negative quantities will become positive and they'll match up. Okay, so let's just do the first two. So you got negative 48 times negative 5 squared plus 3 times negative 5 to the 4th power. Whoa, is that really true? 675. So we've got 5 to the 4th power, 625 times 3, 1875. Then we subtract 48 times 5 squared, which is 25. Get 675. So it is right. Okay. So let's do the next one. Negative 48 times negative 2 squared plus 3 times negative 2 to the 4th power, negative 144. So this will be negative 144. This will be 675. So I think I'm gonna go from plus or minus 1,000. So we're gonna go to 1,000 up here. We're going to negative 1,000 here. We'll go to negative 10, positive 10, and we'll plot those 4 points. So negative 5 is 675. So this is 100, 200, 300, 400, 500, 675. Same way over here. And then at negative 2, it's negative 144. So it's 100, 200, so negative 144 is about there, about right there. The end behavior was from this direction, so we're going to come through here, go through this single root. This is going to be, may not be exactly where it bottoms out, comes up here, loops back around again through this point, through the x-axis, and then zooms up way like that. So that's the function. So let's plot it. So move it over here so I can plot it out. Let's zoom out to 1,000. There we go. Plus minus 10 on the other direction. Looks good. Minus 48 times x squared plus 3 times 4x to the 4th. Graph it. Shift it over here. Pull up our thing. So you can see here at negative 5, the function value is 675, something like that. Same over here. This goes down. Negative 2, which would be about right here. The value of the function is like negative 140 something. So you can see the actual minimum goes down a little bit further. That kind of makes sense, just because this thing has to make some pretty wild turns here to get back around again. So now what will happen is in calculus we'll know exactly what these values of x are that give us these what we will call local minimums. And so that'll help us plot these things much more accurately and quickly. Okay, one more. So it's kind of already in its factored form, so that helps it out as far as doing the next problem. We already know what's happening. One thing is, you know, what is the order of this thing? So you're going to have t times t squared, times t, so it's t to the 4th. So we're going to have t to the 4th, and because of the negative sign, it's going to look like that. So that's the highest order term. So we know the function end behavior is like this, because they go the same direction, but because of this negative sign, they're both going to go down. So that's the end behavior part. The second part is the zeros. Well, we've got two zeros. We've got x equals, well, t in this case. We've got t minus 2 equals 0. That's that one. We've got t plus 2 equals 0. So our zeros from this factor we get t equals 2 is a 0, and this factor we get t equals -2. Now we have a multiplicity. So probably what's going to happen is we're going to come up and hit the x-axis like that, come back down again, then go up again, touch it, and come back down again. So that's what these multiplicity of zeros give you. So we'll use that. So now, what values do I want to choose? Well, I might choose for evaluating the function, I think I'll evaluate it at -3, because that'll give me a point here. I'll do it at +3. Should be the same because it's symmetric. And I'm going to do it at 0, because that'll give me where it crosses the x-axis. Okay, so the function is -1/4 t minus 2 squared times t plus 2 squared. So I get -1/4 times -3 minus 2 quantity squared minus 3 plus 2 quantity squared. So that's going to be -1/4 times -5 squared times -1 squared. So -3 minus 2 is -5. -3 plus 2 is -1. So this is just going to give you 1. 1 squared is -1 squared is 1. -5 squared is 25. So we end up with -25/4. And this one, the next one's going to be the same thing, -25/4. What happens is we'll have 3 plus 2, which is 5. 5 squared is 25. We'll have 3 minus 2, which is 1. So that'll be this. So these kind of switch, and the squares are the same thing. So that'll end up being that. And if you plug 0 in, you're going to have you'll have -1/4 times 0 minus 2 squared and 0 plus 2 squared. So we get -1/4. -2 squared is 4. +2 squared is 4. Cancels out with that. So you get -4. So that's where the function intersects the y-axis. So now we can add a page, put a piece of graph paper in there. And as far as the y-axis is concerned, 25/4 is about 6. So that sounds like our standard scale sounds pretty good. Okay, so the end behavior says things are going to go like this. We have an intercept at -2, +2. We'll plot 2 more points here. So at -3, we're -25/4, which is 6 1/4. 1, 2, 3, 4, 5, 6 1/4. Right there. Same thing on the other side. 6 1/4. For x equals 0, we're at -4, I think, which is going to be right here. So we know that the function is going to be coming this way through that point. It's going to touch the x-axis here because of the multiplicity of that 0. It's going to turn around, go all the way down to -4. Then it's going to loop back up, go back to the x-axis, touch it, but not intersect it. Then go back down through this point and continue on. So I'm going to make a modification to this thing. It's a little steeper than I originally thought it would be. So you can see the end behavior matches what we thought it would be. So that is it. So let's plot this thing. And we're just going to change the scale. So I'm going to zoom in until I get 10, plus or minus 10. There it is. And then we'll plot. So it's going to be negative 1/4 times x minus 2 quantity squared times x plus 2 quantity squared. Graph this baby. And you get that. So now we're going to move that out of the way. We're going to look at our graph. And you can see how it works out pretty good. So here it is. It's, if I stretch this out a little bit, you can see it, x equals -3, that the function is going to be around 6. Same way over here. At x equals 0, y value is -4. So those match up pretty good. Okay, so that's how the cookie crumbles. Leading coefficient test gives you an idea of which direction the function is going to be coming from. You factor the polynomial to find the zeros if you get if you have a multiplicity of zeros. If they are odd numbers of multiplicities, then you intersect the x-axis. If they're an even number of multiplicities, you touch the x-axis. By looking at the end behavior and the x-intercepts, you can usually judiciously select values close to the intercepts or between the intercepts or the zeros. And then once you have those extra points, then you can draw an estimation for the continuous curve through those points.